actually leave me a very good impression due to the very good accommodation here and a very nice arrangement of the workshop. So first I would like to deliver my many thanks to Professor Kim and to the Department of the Mathematics at KAIST. And also I would like to deliver my thanks to Professor Wu to co-organize this workshop. So today I just modified the title of my talks that in the guidebook, in the schedule book, because I just to extend the range and top range of my talks. And yesterday, just I mentioned that I have two affiliations. One is the School of Mathematics Science, the other is the Center for Computational Systems Biology, which is established on the platform where the interaction of the interdisciplinary are encouraged at Fudan University. So actually our center actually is recruiting the new members. So anyone who are interested in joining our team, so can contact me directly. Yeah. So just make a very small advertisement. So this is the overview of my talks, and in the first part I would like to briefly introduce the problems involved the estimation of time delays and parameters contained or embedded in those differential equations, especially the ordinary differential equation or the delayed differential equations. And because we use some kind of special techniques to identify those delays and parameters, so I have to briefly introduce the concept of adaptive synchronization. First is the concept of synchronization, then adaptive techniques. And following, I just to give some representative or typical examples, and including some biological models, and to show the feasibility or the usefulness of these techniques. And in the end, I just want to give a very brief introduction of some other works in our group in progress. Okay. I always ponder the question, what is applied mathematics? Actually, different people have different answers. Especially the people from the community of mathematics usually have a very positive answer, especially emphasize the importance of mathematics. And from their application field, those people always emphasize those application background. But in my mind, I think here the picture gives a very brief idea of applied mathematics. Usually we can get a lot of data through the experiment, and especially nowadays we can get a huge or high throughput data from the experiment. And then to deal with the data, we should use some statistical methods or other methods such as the causality analysis techniques to figure out the interaction between or among the several components or among the several levels, and to show the relationship between these components and the levels. And then with the knowledge of this interaction or relationship, then we can, maybe together with some knowledge from the basic idea from the physics or biology and chemistry, then we can do some mathematical modeling work. So this is very important because most mathematicians focus or pay attention to this area just to do the analysis of mathematical model. So with this modeling, and we can do some analysis First, we can do some dynamical analysis, which will be mentioned later. And also, we can do some, actually, to do some predictions and to predict the possible evolution of phenomenon in the concrete systems. So, with this modeling, and together with the modeling and with the experiment dates, we should refine our models in some cases, because sometimes our prediction is not very accurate. So we have to do some adjustments or modifications. So this is the basic idea of the applied mathematics in my mind. So everyone can has his own idea or opinions on it. So, as mentioned in the last slide, that the mathematical modeling is very important. Actually, here I listed some concrete systems, and require the mathematical modeling. And in these times, I focus on a particular kind of model, and named as the dynamical model. Here is the equations, and usually we use the ft as the state variables, and here the x subscript t and small t is the state variable written in the form of the distributed form, and here p is the parameters that we should identify or estimate it. So here I consider the time delays here, because in most of times, especially in those biological or physical systems, time delay is ubiquitous and cannot be avoidable. So the state usually depends not only on the current state but also on the past state, usually on the discrete state, or sometimes in the form of the distributed form. Just like the current state or the variation of the current state, it depends on the a period of past times. So here is the density functions. If we chose the density function as the direct delta functions, so this form actually degenerates into the simple case as the discrete delay. So with these models, actually for simplicity, I just write the one form of equation here. All the following discussion can be treated the equations just like in the distributed form. Okay, with these models in hand, usually two kinds of questions will appear. And the first question is, what kind of dynamics corresponding to the real phenomenon will the model exhibit for a specific group of delays and parameters? Actually, we want to determine which kind of parameters correspond to which kinds of, and the particular kinds of the real phenomena of biological or chemical or physical relevance. And the second question is inversely, and we may sample or obtain some time series from the concrete experiment, and just we get a time series with the sampling rate. Here denote the rate by the delta. Delta is the sampling rate, can assume to be a very small here. And we want to accurately or swiftly to identify or estimate those parameters embedded in the models, especially here the parameter P, or here the time delays tau. Here is the inverse problem. So the answer to these two questions usually concerns of the first question concerns of the involves of the qualitative analysis, and we want to show in some particular region of parameters, and their model will exhibit their stability, just like the asymptotical stability as mentioned by Professor Wu in the morning, and some kind of the bifurcation dynamics, and even the chaotic dynamics that within those parameter regions, and the model can exhibit a very complex dynamics, and which have physical or biological relevance. So, for the second questions, we usually to build some cost function or penalize the functions, and then optimization of these kind of functions with some specific algorithm, such as the genetic algorithm. So here, I just want to mention there is another very useful technique developed recently and named adaptive synchronization technique, can do the parameter or the time delay estimation. So first, I just to briefly introduce the concept of synchronization or synchronization phenomenon. Actually, we know that the synchronization phenomenon is omnipresent in the nature or in the artificial systems, and maybe the word synchronization is come from the variation grace, but the scientific observation of synchronization is attributed to the Higgins pendulum clock maybe in the early 18th. And so there are lots of synchronization phenomena. The examples above. For example, the sound of the cicadas in the tree in the summer. And sometimes you also maybe you know the story that there may be the flash of a tree, and the tree is replete with a lot of the fireflies. So also you can observe the synchronization phenomenon. And in the neuroscience, there's also a lot of synchronization phenomena, such as the integrate and fire neurons. And each neuron was coupled with inhibitory or the excitedly coupled with other neurons and emit the spikes. And with the time evolution, and the spikes sometimes becomes synchronization. So some synchronization is very useful, such as the group of fish in the sea. And sometimes the synchronization is harmful, just like the internet jam on the complex networks. So this also is very important. But here we should make a good use of synchronization in the parameter identification. Mathematically, we can very simply consider two systems. One is the driving systems, and the other is the response systems and driven system, also named a driven system. Without the coupling, and here the two systems is dx over d2 and dy over dt, and is completely same. Although I write the different variable here for the state variable, but they are totally different if they starting from the same initial conditions. But if they come from the initial condition, different conditions, and the trajectory usually cannot be synchronized, because sometimes due to the non-linearity of the systems, and these two systems cannot completely synchronize. if they do not start from the same initial value point. So the question how to realize the synchronization between these two systems. It is very simple just to add a coupling here. It's a linear coupling. And X is the driving signal and input to the response system. And Y is still the state variable of the response systems. And with this coupling, and it can be mathematically actually validate the complete synchronization between these two systems. Of course, with some mathematical conditions. And here the control gain is some kind of constant matrix. So here both systems have the same parameters and the same time delay tau. So here synchronization is achieved, but the parameter identification cannot be done only by this simple coupling. So we should do some alternative modification. Then here we still have the driving systems, and with these systems generate the time series that we observed. And we artificially to construct a response systems. And in particularly, we don't still use the parameter here because we don't know the accurate value of the parameter of P. Also, the time delays. I omit the time delays for simplicity. So we just to design a new estimator to estimate the parameter P. And also we design the time variant, not a constant matrix, a time variant matrix control gain to be used here to be answer coupling. So we design the adaptive rules as follows. Here it can be seen that the matrix, the coupling matrix, the component of the coupling matrix is monotonic. Actually here is the decreasing. And here the estimator of the parameters is obey these rows. We call these rows as the adaptive rows. So the question is, when the two systems starting from the different initial value, the complete synchronization between these two systems can be achieved. Another question is, the estimator of the parameter can go to the accurate value of the parameter Pi with the time goes to infinity. Here is the question. In a series of papers, they propose this method, and they only validate these techniques for a particular kind of or some typical kind of systems, but they don't prove or mathematically prove their convergence, because sometimes this convergence cannot be completely ensured. So following is our works on these problems and mathematically validate the series of the adaptive synchronization techniques. Maybe here is ASD. I just made a mistake. So in the first two papers, we just prove that under some so-called link conditions, linear independent conditions, and along the synchronization manifold, under these kind of conditions, complete synchronization as well as the parameter identification can be surely achieved globally. And in these two papers, we just to treat the systems which has relaxable conditions, because most systems are not locally Lipschitz, sometimes the locally Lipschitz. And the simply is the x to the power of 2. So it is obvious we relax the conditions here. And also we get the theoretical results on the complete synchronizations, both from the local case and to the global case. And also some work is in preparation and also submitted to some journals and in the process of revision. And we get the results on the parameters estimation for only locally Lipschitz systems. And here the system is much prevalent in the many physical or biological systems. And also we deal with the topic, the time delay estimation as mentioned above. So I just skip the detailed proof of this series and just give a sketch of this proof. And the essential of the proof actually is to validate the boundness, or also called in other words, dissipation of all the trajectories and with some Lyapunov functionals, because we deal with the time delay systems and which has the infinite dimensional properties. So the second step is to determine the final behaviors restricted to the omega limit set of the systems, because Professor Wu in this morning had mentioned that the omega set has a very good properties such as invariant, such as the connected, and especially for those trajectories is bounded, it is non-empty. The first is non-empty. So, and when we restricted on this omega limit set, we can to clarify those final or the eventual behavior, dynamical behavior of these trajectories, and which trajectories can converge to the real value of the parameters or the time delays, and which cannot. So here I give some concrete models. It actually is the toy models here. This is the Mackay loss model, which is introduced as a model for regeneration of the blood cell and the biological systems. And because of the existence of time delays here, and these one-dimensional equations can produce chaotic or chaotic string attractor, because differential equation with time delays can be regarded as infinite dimension of systems, as mentioned before. So here I want to identify or estimate the time delay tau here, which is equal to 3. And the other parameters are known in advance. So with these parameters and time delays, we can generate a sequence of data, a time series. And now we assume that we know the form of the equation, but we do not know the accurate value of the time delays. We want to identify or estimate the time with the time series obtained before. So here I just list some figures of the estimation procedure. And this is the time, actually the state variable as a function of t. And this is the arrow between the two systems. One is the driving system, the other is the response system as a function of t. And here is the estimator of the parameters. So, as mentioned before, with the particular choice choice of the parameters and time delays, the system generates the chaotic string chapters, and also the complete synchronization can be achieved, and the estimate of the time delays also can be accomplished here. So we also try the other form of the time delays, such as the time variant, not the constant time delays, but the time variant time delays. So sometimes this is very important because in many biological, chemical, physical systems, the time delays is not constant, but time variant. So we just tried this method here, and we can see with the very lower fluctuation rate of the time delays, and we also can completely estimate the accurate value of the time delays. But with a much higher fluctuation rate, and the identification cannot be accurately achieved. The next example is a single neuron model. Here, we still to identify the time delays here, and the parameters, other parameters are assumed to be known in advance. And the H is the SIP model functions, which is usually used in analysis of neural networks. So the dynamics of this model with this group of parameters and time delays can exhibit oscillation dynamics. And with this kind of dynamics, the time delay estimation can be achieved in a general sense, which means not accurately estimation can be achieved, but the general. Sometimes some number multiplied by this tau and with the shift. So anyway, this general estimation can be achieved. Also, we try the method to a much larger with the two-dimensional neural network models. And our task is to identify those parameters here, the matrix A and the tau matrix here, and simultaneously. So still, the method is very feasible, and the identification of both parameters and the time delays can be achieved swiftly. Also, we consider the partial estimation. So I don't go to the details of this part. Finally, we consider the case of the delay in the distributed form. This is a little bit different from the several examples I showed before, because just as I mentioned before, there's a condition for the estimations which names the identifiability. And this is very important because sometimes without these conditions in advance, most parameters identification or the time delay identification cannot be surely achieved. Sometimes only in the value or the local region of the real values. So, but for the distributed systems or the system with distributed time delays, it is very interesting that time delay can be achieved even the system has a very asymptotical stability. This is very interesting because with the asymptotical stability of the system without the distributed time delay, usually the estimation cannot be firmly achieved. But here we can do it. We can do it. And we also prove the theoretical result through the dynamical behaviors and properties of the omega limit set. So next, I just to briefly introduce my recent or the latest works on some aspect. The first is because the former examples are actually like the toy models, and we don't deal with the real data. Here we are right now is dealing with the real data, which is recorded from the axons, which is the giant neuron of a snail. So we want to estimate those conductance of the ions channel, such as the sodium, the potassium, and the calcium channels. So this conductance actually is time variant, not constant, keep constant in the concrete experiment. But their fluctuation rate is very low. So we can use some method to accurately to identify or estimate these content as the parameters. And we use the model is the HS model, which named after the Huxley and Hodgkin, who received the Nobel Prize in 1964 maybe. So here's a four-dimensional ordinary differential equation which describes the actual potential of the membrane and generated by this is the giant axon embedded in the squid. And this is the second part of our reason works. Actually, we want to establish or to find out or figure out the mechanism that induce the adjustment of frequency and amplitude in the biological models. Because most biological models described by the ordinary differential equations can produce lots of a variety of the circadian rhythms. And this is very interesting because there's a science paper report, some computational result, which says that with the coexistence of the negative feedback and the positive feedback, and the range of the frequency will be very large. Just like the reason by the mammalian or just the human being's heart rate. And in some cases, the frequency can be very high in some emergent cases. And in some cases, when the people in the silence environment, so the rhythm can be very lower. But the amplitude of this rhythm is almost keep constant. So this is very interesting because we can mathematically modeling these phenomena with some ordinary differential equation just mentioned before. And we want to actually to establish some series for this kind of phenomena. And the tool we used here is the bifurcation series, such as the bifurcations and the homoclonic bifurcations and so on. So the third part here is we want to establish some models of the activity of the chromosomes in nuclei. Initially, we don't to deal with this polymer because it is too long. We only to deal with the DNA as a point in the three-dimensional space. And the aim is to develop or to establish some stochastic models because in the molecular level, all the things are move in the stochastic way, not in the deterministic systems. So we imported some stochastic differential equations, even with some fractional Brownian motion here to describe the evolution of the chromosome and nucleus. Okay, that's all my task.